While we breathe easy on land, the ocean, the source of roughly every second breath, has started to suffocate. Dead zones are spreading where life should explode. Storms ride warmer seas, but it's the missing oxygen that turns abundance into silence. The engine that helps make our air, tiny green drifters, has begun to glitch. Stick with this, because somewhere in this story is your local bay, your dinner, your job, and your next breath. To understand why, we rewind to the microbes. Roadmap of Revelations. We're going to follow the ocean's breath and watch where it falters. First, we start at the climax, mass fish kills. Then pull the camera down to the smallest workers in Earth's life support system, phytoplankton. They're microscopic, but their job is massive, pumping out about half of the planet's oxygen and feeding almost everything that swims. Then we meet the physics. Warm water holds less oxygen. It sounds simple, and it is. Brutal, too. As the surface heats, the ocean stratifies into layers that don't mix. Oxygen gets trapped near the top, while the deep gets starved. Meanwhile, nights, heat waves, and calm spells tip local ecosystems over the edge. But biology and human choices push harder. Fertilizer and sewage spark blooms that crash and rot, and microbes claim whatever oxygen is left. The villains you rarely see. Stratification, nutrients, timing work together. We'll test the decline signal. Satellites reading chlorophyll, ships dragging sensors, and decades of buoy records. We'll weigh conflicting datasets and show where the trend is real. Losses in the nutrient-poor tropics, shifts at the poles, noisy coasts, and we'll anchor it with numbers, like the roughly 0.5 to 3.3% loss of oxygen from the upper ocean since about 1970, and the expansion of the world's low oxygen zones. We'll track the slow creep of deoxygenation offshore, the rise of oxygen minimum zones, and the squeeze on fish between heat above and breathlessness below. Then we'll stack the tag team of acidification and low oxygen, where stress multiplies. Finally, we'll put we can fix it on the table. What works locally, what doesn't scale, and what the physics demands. In-game question. If the ocean can't exhale like it used to, what happens to ours? The breath makers. Phytoplankton 101. To understand the ocean's breath, we need to meet the ones doing the breathing in reverse. Phytoplankton are the ocean's tiny solar panels, single-celled drifters, some with glassy shells, some with elegant whips, all turning sunlight, water, and dissolved carbon dioxide into sugars. The byproduct: oxygen. They do it by the billion, every second, across most of the sunlit sea. Think of photosynthesis like a savings account. Light deposits, energy, carbon becomes stored chemical money, oxygen is the receipt. Meanwhile, everything else, from zooplankton to tuna, makes withdrawals. Balance is everything. When the deposits shrink or the withdrawals spike, oxygen goes missing. Phytoplankton don't bloom on a whim. They live by a global heartbeat. In spring at high latitudes, storm-mixed waters settle, light floods the surface, and nutrients left over from winter mixing are right there. A population explodes so fast you can see the color from space. A green smear off Newfoundland, a turquoise spiral in the Southern Ocean. Then grazers catch up, nutrients thin, and the pulse fades. In subtropical gyres, the big blue deserts, light is abundant, but nutrients are locked below the thermocline. Here, the heartbeat is faint. Small cells with efficient machinery dominate, living close to the edge, recycling every atom of nitrogen and phosphorus they can find. Upwelling coasts are the opposite. Winds lift cold, nutrient-rich water, and blooms roar to life. These regions feed the world. 3 throttles control the show: light, nutrients, and iron. Light is obvious. Nights and seasons write the rhythm. Nutrients, especially nitrogen and phosphorus, set the growth ceiling. Iron is the secret lever. In parts of the ocean where dust is scarce, like the Southern Ocean and the North Pacific, iron starves phytoplankton, even when other nutrients are plentiful. A whiff of Saharan dust can flip a patch of sea from quiet to vibrant. Micro-story. A fisherman from Galicia holds a weathered notebook. For 30 years, he scribbled the dates when water shifts from slate to green, when sardines move in, when the squid lines go heavy. He circles a week in May that used to be reliable, then sighs. Lately, the bloom comes early, or late, or not at all. Timing isn't a detail. Larval fish hatch on a schedule. If the bloom peaks before mouths are ready or after the nursery window closes, survival. Nosedives. The match between bloom and nursery time is a hinge for whole fisheries. Phytoplankton are also engineers of climate. They pull CO2 from surface waters and, through grazing and death, send some of that carbon downward in sinking particles. This biological pump doesn't just store carbon, it helps keep surface waters undersaturated with CO2, letting the ocean absorb more from the air. The oxygen they release mixes into the top layer, then rides currents and winter storms downward, ventilating the depths. Here's the catch. Phytoplankton breathe too. At night, and in the dark ocean below, respiration runs the other way, consuming oxygen. When organic matter rains down, microbes throw a feast, and the oxygen tab rises. Usually, mixing and winter ventilation settle the account, but warm water changes the math. Warmer surface layers hold less oxygen to begin with. They also sit on top of cooler, denser water like oil on vinegar. The seasonal lid, stratification, thickens and the stirring weakens. Oxygen can't easily move down. Nutrients can't easily move up. The photosynthetic deposits shrink. The respiratory withdrawals don't. The account trends negative. Meanwhile, on coasts, we keep feeding the system. Fertilizer and sewage load rivers with nitrogen and phosphorus. Blooms explode, then crash, and the microbial cleanup pulls oxygen towards zero. Add a heat wave, a few windless days, and a spring tide, and you get the silver blanket at sunrise. Stakes? Remove this layer, and food webs stall. Zooplankton lose their base. Forage fish go hungry. Predators chase dwindling bands of survivable water. The biological pump weakens, meaning more CO2 stays near the surface and in the air. The ocean's exhale becomes erratic. Translation: empty nets, volatile prices, failed seabird nests, and a climate that pushes harder next year. A scene from orbit. A satellite pass catches a filament of bloom unspooling off Peru, neon turquoise twisting into cobalt. To the eye, it's gorgeous. To the fleet waiting 12 miles offshore, it's a calendar. They know a few days later, anchovies will ride the edge of that color line, feeding on the plankton wave, unless the wave breaks wrong. And here's where it pivots. Signs point to a world where those tiny solar panels are shifting, towards smaller cells, earlier pulses, longer lulls in some regions, and more violent swings in others. The heartbeat is still there, but the rhythm is changing. If these breath makers power half our oxygen, directly and by setting ocean chemistry, then a slowdown, a mistimed pulse, or a chaotic swing doesn't stay at sea. It follows the currents into food, economies, and yes, the air we share. So if they help decide our breath, why are they fading? To find that answer, we leave biology's engine room and step into the ocean's physics. The decline signal: are phytoplankton actually dropping? To see if the ocean's breath is thinning, we need receipts. The first come from space. Since the late 1990s, satellites have watched the ocean's color shift day by day. Chlorophyll, the pigment that makes phytoplankton green, tints the sea. When it brightens, blooms are likely. When it fades, productivity often falls. It isn't perfect. Color can lie when sediments or dissolved organics muddy the view. But stitched over decades, the trend lines matter. Vast swaths of low-latitude oceans are getting bluer, not greener. On deck, ships drag sensors through the surface and into the dim. Fluorometers sniff chlorophyll. Bottles grab water for lab analysis. Nets catch the cells themselves. These transects don't cover every ocean mile, but they give truth to the pixels. Floats and gliders add the slow, patient heartbeat. Profiles every 10 days, year after year, even in winter storms when ships stay home. Together, it's a triangulation. Eyes in orbit, hands on railings, robots in the dark. So what do they show? In the tropics, where nutrients are chronically scarce, chlorophyll and net primary production have sagged. Warmer, more stratified surfaces mean fewer nutrient injections from below. In the wide subtropical gyres, the desert is expanding. The bluest blues are spreading. Farther poleward, the story tilts. Spring blooms still fire, but timing drifts and community makeup leans smaller. In some subpolar regions, total production hasn't collapsed, but the cast has changed. Tiny picoplankton shoulder more of the work, while big diatoms lose ground. Coasts are noisy by design. Upwelling years punch chlorophyll sky high. El Niño years flatten it. River plumes feed bursts of green that can be food bonanzas or set the table for dead zones. The datasets here fight each other. Some years look like recovery, others like freefall. That's the point. Variability is rising. Fishermen feel it in shorter, sharper seasons and longer, emptier lulls. The Gulf of Mexico's seasonal dead zone, for instance, can sprawl thousands of square miles in midsummer, waxing and waning with spring runoff and heat. Now the caveats, because this isn't a courtroom drama with one exhibit. Satellites see only the top layer and infer chlorophyll from color using algorithms that can drift over time. Instruments age, calibrations shift, atmospheric dust throws off the math. Even the definition of trend depends on which years you choose. Early studies flag global declines. Later reanalyses softened that to regionally mixed with deserts growing. But independent lines keep pointing the same way in warm, stratifying waters. Less nutrient supply, smaller cells, lower net production. Lab cultures add a different lens. Warm a diverse plankton community, and you don't just speed things up, you change who wins. Many large silica shell diatoms run into nutrient stress sooner. Small cyanobacteria hold their ground. Diversity drops, and with it, resilience. That's not a global ocean in a beaker, but it echoes what ships and satellites report. Here's where the signal touches dinner plates. In systems like the California Current and the Humboldt, years with weaker, mistimed blooms leave anchovy and sardine recruits thin. Larval survival collapses when the plankton menu shrinks or arrives off schedule. Seabird breeding fails in lockstep. Trawlers read the echo sounder and see the squeeze. Prey fish pressed into narrow bands where temperature and oxygen still cooperate, then gone. And remember that chlorophyll isn't oxygen itself. It's a proxy for the engine that sets oxygen's budget. In nutrient-poor seas, fewer phytoplankton mean less photosynthetic oxygen added to surface waters and a weaker biological pump. In eutrophic coasts, spikes in chlorophyll can be the first step toward a crash in oxygen debt. Both ends of that spectrum can leave the water gasping for different reasons. What about counterpoints? Regions where productivity is ticked up. They exist. Melting sea ice has opened light to some polar shelves, briefly boosting blooms. Dustier skies in certain years deliver iron that wakes up high-nutrient, low-chlorophyll zones. But these are patches and pulses, not a blanket reversal. Many gains look fragile, dependent on short-lived conditions, and vulnerable to the next marine heat wave that can slash chlorophyll and reset communities towards smaller, less nutritious cells. Speaking of heat waves, the ocean's new extremes make trend detection harder and more urgent. A marine heat wave can slash chlorophyll for weeks, then the average recovers on paper while the ecosystem doesn't. Corals bleach, kelp forests shrink, the plankton community resets to smaller, less nutritious cells. The baseline ratchets even if the line looks flat. One detail will matter later. As cells get smaller, they change not just how much carbon they fix, but where it goes. Small cells tend to recycle in the surface. Their carbon lingers, feeding microbes that respire oxygen away right where stratification is strongest. Less carbon sinks, so less oxygen rides downward with ventilated waters. The oxygen account gets squeezed from both sides. Fewer deposits, harder transfers. So, are phytoplankton actually dropping? The fairest answer is, in many warm, nutrient-limited regions, yes, the desert is growing, communities are shrinking and shifting, and timing is slipping. In colder, dynamic regions, the pulse is changing in ways that can still starve nurseries and scramble food webs. On coasts, volatility is the new norm, and volatility kills predictably. We've taken the pulse of the breath makers and heard a stutter. To understand how that stutter turns into silence, the missing oxygen itself, we have to leave color and counts and step into chemistry and physics, where warm water, layers, and nights decide who breathes and who doesn't. Warm water, less oxygen, the physics that suffocates. To see how missing plankton turns into missing breath, we need the rule that never blinks. Warm water holds less oxygen. Take 2 glasses, one cold, one hot, shake in air, and measure. The cold glass stores more oxygen molecules between water molecules. Heat jostles them out. The ocean is the same glass, just bigger. As surface waters warm, they start with less oxygen to give. Now add layering. Warm water floats on colder, denser water. That top layer forms a lid, a stratified cap that resists mixing. In winter, storms and cooling punch oxygen downward, but as the climate adds heat, the lid thickens and the punches land softer. The ocean's conveyor for oxygen slows. The deep keeps breathing out carbon and using oxygen, but the resupply from above gets starved. This is where the day-night cycle becomes a gambler's coin toss. In sunlight, phytoplankton add oxygen to the surface layer. After dark, everything respiring, plankton, fish, microbes, draws oxygen down. On a hot, breathless night with no wind, that drawdown can outpace the day's deposit. By dawn, the line crosses a threshold and gills fail. A single still night doesn't cause a dead zone, but it closes the gap. Stack a heat wave, a spring tide that slacks currents, and a recent bloom, and the physics tips the biology. Mixed layers, the depth of that surface cap, are shoaling in many places. Shallower caps mean the day's oxygen stays trapped near the top centimeters, saturating quickly and bubbling back to the air instead of ventilating downward. Meanwhile, the dark waters below keep respiring. The mismatch grows. Production up top can't reach demand below. The account bleeds. Wind matters more than we like to admit. Trade winds slacken during certain climate swings, and local calms are stretching longer. Less wind means less stirring, less oxygen injection, and more time for consumption to run ahead. Marine heat waves supercharge it. Warm anomalies can raise respiration rates and lower oxygen solubility at the same time. A 1-2 hit. During the 2013 to 2015 warm blob in the Northeast Pacific, oxygen at mid-depth sagged while the surface cap hardened. Fish and crabs squeezed into ever-thinner bands. Then there's the slow creep in the open ocean. Oxygen minimum zones, natural midwater layers where oxygen runs low, are expanding and rising. The reason loops back to physics. As surface waters warm and freshen, they mix downward less. The interior receives less oxygen, but organic matter raining from above still decays, consuming what's there. Since about 1970, the upper ocean has lost on the order of 0.5 to 3.3% of its oxygen content, and the minima are thickening and shoaling toward the layers where tuna and billfish hunt. Predators get pinned between heat above and hypoxia below. Case study, quiet and devastating. A calm August week on a temperate shelf. A recent heat wave kept the mixed layer razor thin. A modest bloom flared and faded. Nights ran warm, winds slept. By the third dawn, oxygen meters on a pier ticked down to stressful levels. Crabs crawled up pilings. Eels surfaced. A gusty front finally turned the water over, rescuing the shallows while pushing low oxygen water laterally along the bottom. A mile away, a cove woke to a fish kill. Now fold in the invisible arithmetic of respiration. Warmer temperatures increase metabolic rates. The Q10 rule of thumb says many biological processes speed up with heat, often roughly doubling with a 10-degree rise. That means for the same unit of organic matter, microbes burn oxygen faster in warm water. So we start with less oxygen, mix less of it down, and use it faster. You don't need catastrophe to lose the bet, just a few percent in each factor aligned. Coral reefs know this math by feel. Heat waves push corals to bleach, expelling symbionts that feed them. Nighttime respiration in stressed reefs can pull oxygen low enough to add suffocation to heat stress, especially in enclosed lagoons. Similar spikes hit kelp forests after marine heat waves. Canopy loss slows local mixing, and decomposing detritus quietly taxes oxygen. There's a twist that looks like good news, but isn't. In shallow, sunlit waters, photosynthesis can oversaturate oxygen, briefly pushing concentrations above 100% relative to air. It sparkles as bubbles on algae, but when stratification is strong, that surplus vents back to the atmosphere instead of diving down. The deep still waits. You can see how nutrients turn this screw even tighter, but hold that thought. The physics alone, lower solubility, stronger caps, shallower mixing, faster respiration, moves coastlines and midwaters toward thresholds they used to flirt with only on rare nights. Cross them more often, and biology starts writing new rules for who lives where and when. Now add fuel, and the floor drops out. Nutrients, algae, and the nighttime heist. Here's the fuel we've been holding. Nutrients. When rivers carry fertilizer and sewage to the coast, they don't just color the water. They load it with nitrogen and phosphorus, the very throttles phytoplankton crave. Sun comes up, the lid is strong, and a bloom ignites. An emerald switch flipped across a bay, a delta, an estuary mouth. Fishermen cheer at first. Nets go heavy with grazers and baitfish, but blooms are burst by design. They peak fast, then the real heist starts at night. When the algae die or get grazed into tiny particles, microbes take the stage. Their feast is chemical, relentless, consuming organic matter, inhaling oxygen, exhaling CO2 and acids. In a stratified system, That decomposition doesn't ventilate away. It pools near the bottom, peeling oxygen off hour by hour. By the second or third calm night, hypoxia, low oxygen, arrives like a curfew. Add another day or a spring tide that slides low oxygen water sideways along the seabed and pockets tip into anoxia. No oxygen at all. Hypoxia and anoxia aren't the same neighborhood. In hypoxia, many animals still move, but sluggishly. Behavior changes first. Shrimp lift from the bottom, fish school tighter, seeking thin ribbons where they can breathe. In anoxia, movement stops. If sulfide-producing bacteria bloom, common when oxygen has gone long enough, water takes.
On that rotten egg smell. That's hydrogen sulfide, a toxin that shuts down respiration outright. It stains sediment black and burns gills. You don't mistake this for anything else. Now map it. The Gulf of Mexico's seasonal dead zone forms where the Mississippi delivers a continental diet of nutrients. After spring planting, rains flush fertilizer downstream. Warmth arrives, stratification locks in, and blooms flare across the shelf. Weeks later, bottom waters read like a slow-motion asphyxiation, often spreading across several thousand square miles until storms remix the layers. Shrimpers, seeing oxygen forecasts, steer for the edges, spending extra fuel to chase the surviving bands. Catches get weird. Lots one day, nothing the next, as fish slip ahead of moving fronts of bad water. Across the Atlantic, the Baltic is a different machine with similar results. Its semi-enclosed basin and limited exchange with the North Sea trap nutrients and strengthened layering, especially after mild winters. Hypoxia, there isn't just seasonal, it can persist year to year over large areas of the seafloor. Historical overfishing thinned top predators, shifting food webs toward more plankton-fueled cycles. Sewage upgrades helped in places, but legacy nutrients stored in sediments still leak back, a memory the sea won't erase quickly. The Black Sea and parts of the East China Sea tell kindred stories. Rivers, warmth, calm spells, blooms, and the same nighttime arithmetic. Micro story. A captain out of Houma, Louisiana, stares at a handheld meter. It reads 1.6 milligrams per liter, below the 2. Migden Lober fouls in differentiations. It a line where his crew starts worrying. He hauls his trawl early, moves 10 miles east, checks again, 3.4. They set, pull, leapfrogging a boundary that slides under the dark like an invisible fence. Back home, his kid's soccer practice gets rained out by the same storm that finally breaks the cap and saves his week. The link runs from field to river to net to kitchen. It's tempting to call this a problem of too much algae, but the villain is timing plus stratification. The same nutrients in a windy, well-mixed system might burn through without bottom water suffocating. In a lidded system, those nutrients light a fuse, and the CO2 produced by decomposition adds a second stress, lower pH in bottom waters. Acidified low-oxygen water makes it harder for clams, oysters, and juvenile crabs to maintain shells and for fish blood to carry what little oxygen remains. That's the double hit many hatcheries learned the hard way, buffering intake water just to keep larvae alive. Zoom in further to the nightly cycle. In shallow estuaries, daytime photosynthesis can spike oxygen above 100%, giving noon a false sense of safety. After sunset, the same biomass flips, respiring alongside everything else. With a strong cap and no breeze, oxygen drops like a rock. By dawn, crabs are at the surface, their antennae breaking water, and egrets hunt fish that can't flee. One missed wind event, one extra warm night, that's the margin. Can we pull this lever back? Yes, locally. Cities that upgraded wastewater plants saw bays brighten and stay breathable longer. Wetlands stitched back into river mouths shave peaks off nutrient pulses and slow the surge. Farmers who keep cover crops and time fertilizer to plant uptake send less nitrogen downstream. These are not silver bullets, but they are breaks that work. Because here's the uncomfortable line through it all. The physics set the stage, but nutrients pack the theater. Warm water lowers the ceiling, stratification locks the doors, nighttime respiration turns off the lights. Add fertilizer and sewage, and the audience rushes in, breathes hard, and the air runs out. And that's just the coasts. Offshore, where no river pours, another kind of heist is spreading in slow motion.